Hello, everyone. We are happy to welcome Euihun second time to this seminar series, and this will be seminar number 30. And Euihun will be talking about his recent work, which we find very interesting. It's about worldline higher speed gravity.
So I will talk about my recent work in collaboration with my student Minkyu Cho, and also my ex-student who is postdoc in KIAS, Tae-hwan Oh, and also Tung Tran, who is also doing postdoc in the group of Kyung University, theory group of Kyung University. So this work was just published like a month ago, and it is about the worldline higher spin gravity. So I assume that more or less everybody here knows or have certain idea about what is higher spin gravity. So I will not give detailed introductions about the theory. So the work is actually about the question whether we can have some microscopic descriptions of higher spin gravity, something like a string theory, if you like. So indeed, actually, higher spin gravity, which is constructed by Vasiliev using his highly non-trivial equation. This theory was viewed as some toy model for tensionless limit of string theory because it contains infinitely many massless fields, massless fields. We know that in the tensionless limit, all the string states will become massless. So that's a similarity. But on the other hand, it contains only symmetric tensor fields, symmetric massless higher spin fields. So compared to string theory, it's drastically simpler. So even though it contains infinitely many fields, actually it is infinitely simpler than string theory. So then we can, about higher spin gravity, indeed, it is formulated by Vasiliev theory. Nowadays, we can also view this theory through holography. But anyway, if you look the Vasiliev theory, the theory itself is elegant and it contains a lot of informations and non-trivial structure. But nevertheless, several questions are not very easy to answer, such as action principle or locality issue. So in that sense, in that regard, probably it would be very nice if we can have some microscopic descriptions of this higher spin gravity, something similar to string theory. Then maybe this new way to see the higher spin gravity may give us new insight and new light on these kind of difficult questions. So if you just think that whether if higher spin gravity can be described as some sort of worship theory, well, one can think about that it is a kind of closed string because it contains actually the gravity. But on the other hand, one may also think it is an open string because actually we know that all higher spin, all the spectrum of a higher spin gravity can be matrix valued, extended to a matrix valued field, which has the same well, that is the future that OpenString has. So that apart from that kind of some general idea, not so many concrete proposal or concrete work has been done in this direction. I think the only exception is this old work, relatively old work by Enquist and Sundell. That I will come back later. But anyway, here again, the idea is that in the tensionless limit, all this closed and open string even brain becomes tensionless, and then it reaches the boundary of AdS, and if there is a new effective descriptions of this degrees of freedom, and then somehow new description emerges. That's the what they proposed, and then that I will maybe come back to this in the later part of the talk. Okay, here instead of worksheet, we will actually focus on the word line descriptions. Whether indeed actually word line can be used to describe any kind of particle species. So for that we need to introduce certain amount of constraints. So has a long history and many people worked on this side. So we also had a recent work on this issue. And otherwise, we know that the clear limitations of this worldline theory is that it describes only free theory. Of course, we can put this worldline on a non-trivial background, but the worldline degrees of freedom
No,
itself
there.
is free, and we cannot easily add interactions. For interaction, in principle, we have to introduce this kind of junction by hand, and then we need to assign how the word line fields or how word line degrees of freedom should be connected on this junction point. So this is some external information. Otherwise, we have many results on this word line theory. For instance, vectorial means that the usual space-time variable x mu like things. The description in terms of x mu is available. Otherwise, we can have also the twistorial description. That is what we will focus on. So this twistor description is defined only in particular dimensions. So it's limited, but it's actually not that limited because in all interesting dimensions, somehow proposed by string theory that proposed by supersymmetry just goes well with this twistor. So yeah, anyway, so it is available in particular dimension, and it's typically much simpler than the other description because it contains a fewer number of a smaller amount of constraints as a constraint system. Another limitation is that its variable do not contains position variable. So that's why connection to space-time should be made through some relation like incidence relations. Here I didn't put any citation because there are so many works in this twistor stuff. But for us, what we like to have is the massless fields in AdS, especially massless field in AdS4. Luckily, those are also studied well in the literature. Typically, Sedevar and also many other people worked out, but much less compared to actually flat space-time. So in particular here, Sedevar had considered the one simple action which contains only massless worldline twistor actions, which describe a massless spin S field. But if you remove from that action the spin constraint, because the action itself is worldline action is a mechanical system with some certain constraints, and one of the constraint is nothing but it's just picking certain spin S. And then if you remove that constraint, he proposed that probably then actually the theory, the worldline theory should describe the spectrum of higher spin gravity. So not only spin 0 or spin 1 or spin 2, but the whole entire tower of all those things. So especially for in AdS4 case, actually the only constraint the theory, this worldline twistor theory has is a spin constraint. So if you, after removing spin constraint, actually there is no constraint. So the theory becomes practically trivial or almost trivial or super simple if you like. So this is the theory. So the theory is just this type. There is no constraint and only their Z type. And then this is typical way to write down this the twistor action. Capital A is takes 4 value. Alpha is 2 value. And then altogether zeta, this xi and pi altogether it takes 4 value because it is AdS4 isometry is SP4. So something like that. But you can see that on top of this alpha or A index, there is other index which I denote as 1 and 2. So this is, if you can interpret as internal index or dual index. This is a certain amount of this, I mean, this index is needed to describe massless fields in AdS4. So in that, so this index, in a sense, with this index, you introduce two twistor instead of one twistor. So that's why sometimes this model is referred to as two twistor model. And then this omega is nothing but this symplectic form. given simply by this matrix. And after suitable integration by part, we can write down this action as this simple form once again. Again, this, if you like, this is just a PDX type. PDX type. And then no Hamiltonian or nothing, just PDX alone. So it's really super simple. So since the classical theory is super simple, we can also quantize it almost trivially. We can do in many different ways, but we can also consider path integral. So we can consider the transition amplitude from state psi1 and psi2, which is connected by this word line I, and starting point Si and ending point Ei, which is the point. Then actually the path integral can be simply written in this way, and this should give us this transition amplitude. But since this section do not have any Hamiltonian, it's trivial, Hamiltonian is trivial, actually this path integral is almost trivial. It just reproduces each time some kind of delta functions at its discretized time. Eventually it reduces to this ordinary integral. And in a sense that this is nothing but just inserting some completeness relation in between these two states. This is nothing but the fact that if you do quantize the theory canonically, because the theory was PDX type, yeah, canonical quantization means just the p hat and x hat is our variable, and the only thing we have is the only structure we have is on just this one. So canonical quantization would be enough in principle for practical purpose, but for the conceptual view, perspective is useful to have in mind this path integral picture for later interacting case. So this, so indeed, after quantization, we have, so actually one more comment is that we chose we did integration by part to make the action in this form, because in this form, derivative is acting on pi, that means that actually we can take the boundary condition on pi, because this is one derivative type, so we can impose boundary condition only half of the variable. So with this, we can, the boundary condition will be on the pi side, or if, in other words, we can choose wave function as functions of pi. So then this function of pi is nothing but the Hilbert space of, or one particle Hilbert space of higher spin gravity. It should contain spin 0 to spin infinity, everything. And then if you wanted to see that how spin is sitting inside of this Hilbert space, we can consider back the spin constraint, which was originally not this shape. It was originally this variable, but after quantization, it becomes simply this differential operator. And then if you restrict a certain eigenspace of this spin constraint, then you go to certain spin S sector. But if you don't consider any eigenspace, then actually you have your Hilbert space contains all massless higher spins. And one thing to note is that actually this S is just kind of number operator, so it can have some integer or half integer eigenvalue. But what some subtle thing is that actually plus S and minus S correspond to the same spin S irreducible representation. So plus S, taking plus S value and minus S value, actually it is the same spin S, but just somehow sitting in this Hilbert space with multiplicity 2, if you like. So, and then on top of that, what we can do more is actually you can see actually it has AdS-4 isometry. Otherwise, because if we don't talk about these things and also spin constraint, everything is just a PDX. So we don't see any structure. So in a sense here, we have to assign the space-time structure or certain structure that we want to work with, in a sense, a little bit by hand. And for that, what we can see is that indeed the AdS-4 isometry can be nicely acting on this space. Or this can be also treated in classical level. in terms of a pi and xi variable. But after quantization, this acts, all this space-time symmetry acts as this differential operator. And remember, so this is written in a SP4 friendly language, which is nothing but SO2,3. And then this translation, remember that, okay, this, oh, sorry. So this translation is not the entire four-dimensional AdS4 translation, but only a boundary translation. So for the additional translation, we need to just choose one of the generator in L actually. So anyway, so up to this point, things were kind of known and people did understood. And you see that this is essentially going to the representation theory of this SP4R. And then we can see that, okay, this space contains all massless higher spins. So what we did first on top of these things is that we wanted to look really some more concrete spiness things, spiness also some more physics rather than just representation theory. For that, what we could do is that just we follow Weinberg textbook. If you know the Weinberg QFT textbook, he start from the representation and construct field operator by making use of space-time covariance. So we can do the same thing because we have representation and we know how symmetry acts on this representation space. So this information is enough to repeat what Weinberg did in his QFT book. So we did first in the Scala case. So Scala case. So before that, just let me just again review the thing. So the quantum operator, a field operator, should be covariant with respect to AdS4 isometry. In particular, translation covariance, we should relate some field in some reference point to arbitrary other point by this translation. You see that here this is three translation, and so this is the extra direction translation. If you like, if you think in terms of AdS boundary, AdS like this. So P is acting this side, and then D is acting this side. So both are translation. So P is like tangential translation, if you like, and then D is radial or normal translation in AdS4. So and then so that naturally the choice of this P and D as our translation vector, translation generator, lead to the Poincare chart. And on top of it, this field in the reference point, this reference point can be regarded as the origin of this coordinate. And then we can ask Lorentz covariance, or if in case of Scala field, Lorentz invariance. Then actually this operator should be quite severely restricted. In free field theory case, practically it's determined. So we know that the free theory case, so this field operator will create one particle or annihilate one particle. That's why if we act this field operator on vacuum, it will make one particle state, which is nothing but a certain state in this Hilbert space. So in this way, we can try to find it. So that's what we did. So for instance, we take Scala field. The Scala field acting on this vacuum should be one particular state. That should be functions of pi. So indeed, this state we will try to identify as functions of pi, because functions of pi is some state in one particular space. And then using translation, this can be identified related to the same thing in the reference point. And this reference point, this, if you like, wave function or this free field operator, is subject to the invariance with respect to Lorentz symmetry. So this one, which is actually nothing but a differential operator. So once again, this kind of construction is precisely something that you can find out in the Weinberg book, if you like. So, and then the result is that so now it just is sufficient to solve this differential equation, and solution is given by this form. And then here you can first note that actually it's not fully determined. It's given with a C plus and C minus with the two constant. So it's not completely determined, but it's almost determined. And another technical remark that we can make is that actually the function is Gaussian type because pi is the kind of pi sees the operator nature of these guys, and then the nature is actually Gaussian function, if you like. And then now you can also check retrospectively whether this is the good free scalar field. And then for that, we can check whether it satisfies certain Klein-Gordon equation in AdS coordinate. And indeed, you can check it satisfies Klein-Gordon equation with a certain mass. And this mass value is nothing but the conformal scala, which is the scalar field sitting in Vasiliev theory. So now what we can do? So what we can do is that since we created this one particular state, we can consider the norm or inner product, if you like. So that for and then we can construct we can compute a two-point function. So for that, it's just sufficient to do this integral, or if you like, this is essentially inserting this completeness relation in between these two in this in the middle of this here, because this will be anyway one particle state and this is one particle state. So we insert here one particle completeness relation. So then anyway, so in the end, so this is, as I told you, that this is a Gaussian function and this is Gaussian function. Product of Gaussian function is Gaussian function, and Gaussian integral of Gaussian function is easy to do, easy to evaluate, and we end up with this expression. And everything is organized nicely, and we obtain result in terms of this distance function, sometimes called chordal distance, and which is in this Poincare coordinate. It's written in this way. And here, note that here we are in bulk of AdS. So this is really bulk two-point function, and which is not surprising. We are dealing with the free field. So just AdS4, free two-point function. And then we have a bunch of this coefficient, certain combinations of coefficient and also other contribution. And then now we can see that how we can determine this plus and C minus. And we see that these two functions has or if you can just look the boundary behavior, I mean small z behavior of entire functions. And if we choose C plus and C minus to be equal number, then it kind of add up. And otherwise, if you choose oppositely, then it kind of cancels out. And then it actually leading behavior of each of these part cancels out, and it corresponds to Neumann boundary condition. So for this conformal scala, actually both Dirichlet boundary condition and Neumann boundary condition is a good one. So actually we don't need to choose we don't need to choose, for instance, just Dirichlet, but we can also choose Neumann, or some mixed one is also a good one. And eventually there will be one degree of number C, for instance, even after fixing Dirichlet boundary condition, C plus will be undetermined, but that can be determined by some canonical commutation relations, or if we want to do AdS-CFT, again by comparing CFT data and CFT, we normalize the point function. So the final remaining the constant is not really genuine freedom. So other thing that we can note is that indeed we have this distance and some other distance, which is the distance between one point but with the minus z and the other point. So this weird point with the minus z value, in principle z is positive number, so we cannot put any minus number, but we may interpret it as a kind of mirror image. So it's like the AdS boundary is a mirror. So this point is some point just something which exists across the mirror. Or if you can also interpret it as antipodal point. So either the interpretation is okay, but anyway, the computation is just here 1 minus z. So here, instead of z minus z prime, we have a z plus z prime. So anyway, so for Scala, we computed two-point function and we checked that it satisfies Klein-Gordon equation. We did what we wanted to do. Good. So this was we repeated what Weinberg did in a sense more, and then we moved to spin-S case. Actually, if you look the spin one example of massless spin one example of this kind of construction in Weinberg book, you see the problem because we cannot impose any more Lorentz covariance because the massless field is not transforming really covariantly, the quantum massless spin one field. Because upon acting the Lorentz symmetry, it transform with certain gauge transformations. So that's why somehow we can also justify why gauge transformation should be there. Anyway, that's kind of thing can be we can learn very well from the Weinberg book. But here we wanted to avoid that kind of complication, so that we wanted to construct immediately the gauge invariant quantity. So that will be the good one will be spin-S wire tensor. Spin-S wire tensor is nothing but S derivative, so it's kind of curvature made out of a Frontstadt field, but we take a traceless part of it. That contains genuine degree of freedom, and it's kind of equivalent way. We can, instead of working with Frontstadt field, we can work also this spin-S wire tensor. That's just another choice that you have. So this wire tensor can be splitted. This is two-row-Young diagram, traceless two-Young diagram in 4 dimension. So it can be split into self-dual and anti-self-dual parts, and C plus n and C minus s. They are complex conjugate to each other. And we will try to identify these guys. But they are self-dual. For instance, if we focus on the C plus s, they are self-dual field. We don't need to identify all their component because some of their components will be related to other ones by duality. For that, it's sufficient to just focus on transverse components. So that's why it's okay to work with the index, which is actually SL2R tensor. It's like boundary tensor. If you like, this has a component which is mu nu type, boundary type, mu nu, also Z type. But all the Z dependent component here can be removed. We can remove it by using this self-duality. So then we just work mu nu type, which is nothing but the tangential index. So this boundary tangential index, this tangent is a three-dimensional space, and then that traceless tensor in 3 dimension. This is just SL2R in twistor form. So it can be described as this symmetric rank 2S tensor. And then, so this is self-dual, anti-self-dual, they're complex conjugate to each other. And on top of it, we will use another, standard trick in working with a higher spin, which is the introductions of some auxiliary variable. So in this case, we introduce this V to contract this index alpha. So the V can be understood as a polarization spinner, if you like, because actually for spin 1, we need to introduce 2V, right? Kind of polarization vector, but it's again square root of this polarization vector, if you like. So good. So now we have all this set up, and we repeat exactly same thing. So we impose that this function to satisfy translation covariance, and top of it Lorentz covariance. For the Lorentz covariance, we know that this is not Lorentz invariant, but actually we know that self-dual part is with respect to Lorentz, it will be invariant with respect to half of Lorentz, but the other half of Lorentz should transform as certain rank S tensor. So with that information, we can completely fix once again, not completely, but with some coefficient, all these guys, and then we have identified this expression. So now what we can do, we have to satisfy what we have identified is the good one, and indeed what we can check that they satisfy Bargmann equation, which is the equation equivalent to Frontstadt equation. Indeed, they then This means that they describe massless spinous field in AdS4. They are good. So and then we see that they are all is again Gaussian function. So this is again under technical remark. And the final thing is that each of these, for instance, self-dual field comes with a two coefficient, two constant, and anti-self-dual another two constant. But then we know that we have to impose a proper boundary condition, and differently from spin zero case, spin S case, actually only Dirichlet boundary condition is the good one because other boundary condition will violate unitarity. So we impose Dirichlet boundary condition, but then actually that reduce this coefficient, which were 4, into 2, C plus and C minus.
Ayhan, sorry,
And
I forgot to ask.
yes,
Would you mind to have questions during the talk or
sorry?
only at the end? Would you mind to get questions during the talk or at the
Yeah,
end
yeah,
only?
yeah, no problem.
Okay, I think Zhenya has a question. You can
Yes,
ask.
Yeah, hi, Han. Many
yes,
thanks for the talk. So don't have to go to Yerevan. So you have wild tensors, but to introduce interesting interactions, you need gauge fields.
yes.
How you gonna reproduce any gauge field like Fronsdal in this approach? Thanks.
Yeah, I thought about it. So here, the first answer is that this construction only see the end result. So even though the interaction can be mediated through the gauge potential, but but the physical data can be, or if you like scattering amplitude or this kind of things can be extracted only from the Weyl tensor, even though certain scattering amplitude should be mediated from the kind of gauge potential interactions. But this approach somehow we don't. So the interaction is coming from this worldline picture, not from the really field variable. So that's why I think it's just safe to just work with this guy because this is essentially our just only it's just observable that we take. So that's the first answer. And second answer is if we wanted to. So I wanted to see whether this kind of setup can be connected to Vasilyev's theory. And in that regard, indeed, it will be good if I can also define Fronsdal field in this way. Then I think I thought that then probably I have to introduce some kind of unphysical Hilbert space, which accommodate the degrees of freedom of gauge potential. I mean, inside of gauge potential, there are huge gauge degrees of freedom. So probably I have to double something like that. But I don't have any progress, so I didn't push my sort of on that direction. Yeah, okay, so I will then proceed. So another comment here is that actually I told you that the spin constraint should not, one should be careful because actually this self-dual is essentially helicity plus and this is helicity minus. But you see that this plus is actually plus S eigenvalue of spin operator, and this is minus S and minus S plus S. So this spin constraint, which is actually whole dual operator eigenvalue, is not actually related to helicity. So it's kind of there is some sort of mismatch or kind of weird linear combination issue here. So that is something tricky which you should be careful. So otherwise we can again go to compute a two-point function. Again here, it's a Gaussian function, it's straightforward. And then if we compute C plus and C minus one, we get this one, and C plus, we get the other, this one. And there is other plus minus and minus minus one, but I just suppressed. This P is given by this structure, which is kind of familiar. And again, we see that C plus C minus is just coming in this way. So we see that there is no way to actually determine C plus and C minus how they should be because it appears only in this kind of in this combination. So with the two-point function, there is no way to distinguish these two, choose uh, C plus and C minus. And the one comment that I can make here is that actually this was, I spent a quite long time in understanding this result, which is just a simple result that you don't need to do this word line, but you take your any favorite way to address the spin-S computation or spin-1 computation. Do anything spin-1 two-point function computation in AdS-4, then you should get this kind of result. But this is surprising because you see that, so this is plus LST, and this is upon complex conjugate, it's plus LST to plus LST propagation. And this one is plus LST to minus LST propagation. So somehow plus LST becomes minus LST, and then the propagation is not zero. So this does not take, this never happens in flat spacetime, but somehow in AdS this takes place. So I thought that this was weird, and then I had to spend a really long time to understand this issue. How come that there is without any interactions, plus and LST becomes suddenly minus LST? What happened? And the clue comes from actually this one. There is this minus Z. So this, I told you that this is mirror image. So I think we should understand this. Plus the helicity become minus helicity because it can bounce off from the boundary. And then after bouncing, the helicity flips. And that's why we have not this kind of non-zero two-point function. And surprisingly, this could be even the fermion spin one half, this kind of phenomena exists, but I think it was not discussed in the literature.
Hi, Han, just a small comment
Yes.
because we had similar issue with Richard and also spent a lot of time. There is a vast literature on chiral symmetry breaking. That's exactly spin half story, and people noticed it in the early days of AdS-CFT, that it flips the chirality, blah, blah.
Oh,
and
I see.
there are gazillions of papers. We cite some of them in some of
Okay,
the recent
okay.
papers just because it was also important. Yeah.
Could you tell me the keyword about that?
It's called chiral symmetry breaking, but in AdS. I think
Chiral symmetry breaking in
chiral
AdS.
symmetry breaking. Yeah, I think Paratti had one of the first papers on this
Oh,
business.
I see, I see. Maybe I didn't manage to find the right references. See, nowadays, AI cannot answer everything. I tried to look many things, also using different kind of AI or different model, but anyway, okay, good. Thank you. So then now let's go to interacting case. So for the interaction, since our theory is worldline model, in order to introduce interaction, we have to introduce junctions, and then again we have to introduce the method, how to glue things here. So for the concreteness, let's consider this Y junction or three vertex interactions. So the transition amplitude is that originally we had a psi1 to psi2, but I prepare another state, psi3, and this should somehow interact here and then provide some sort of transition amplitude. And then naively we can cook up prepare this kind of things, and then path integral should be there, and then path integral should involve some information to what to do on the junction point. And on the junction point, only half of this z variable, either pi or psi or the other kind of half, should be assigned around here junction point. And then yeah, that's should be the rule. So once again, to recapitulate the situation, indeed, all this happens because worldline theory is free. So in general, there is no built-in information of this junction condition. You have to do by hand, and probably if you do slightly wrong way, probably you end up with some physically unnatural or unacceptable result. I don't know. Yeah. So something which we have to do by hand afterwards. But actually, the situation is similar in string theory. If you see string theory, vertex theory is actually free. It's a two-dimensional theory. It's just free theory. There is no interaction. But actually, the string interaction is again it's the same nature. But we know that the junction condition again like three strings, and then how they glue. I mean, this is just they glue geometrically, just smoothly and nicely. That's the junction condition. So no more condition than that. So maybe an analogous junction condition can be used for this worldline twistor. So that was the whole point. of this work. And then for that, we note again, when we consider this kind of path integral, this twistor variable is actually a two twistor, one Z1 and Z2. So here the twistor index or A was kind of suppressed, or here it's written, but anyway, the good important distinction is this other index 1 and 2, which is I refer to as internal or dual index. So a priori this is like the same word line, but two different twister is living. But we can interpret these things slightly differently. So instead of two field defined on one word line, I can say that same field, one twistor field defined on two word line. So if you write down the action, it's the same. Action is the same. We cannot distinguish these two. But somehow geometrically, if we do this, it's much easier to think how to glue things. It becomes a bit more intuitive. So in this way, now if you have three things, like the picture I have in mind is this one. So now all the line is double line, and then now it's we can just glue blue line to blue line and red line to red line. But here I have some problem because I have to glue this line to the red line to blue line. So I can smoothen out the picture. Again, here I have some issue. Here red line and blue line. So in order to glue smoothly these ones, we can do in principle some operation on I3 side. So if I of this word line, and also the color is kind of at this stage it's just some not yeah some way to distinguish the different word lines 1 and 2. Actually, this different field 1 and 2, 1 and 2. 1 is blue and 2 is red. But here I can just also I can change the color. So then this line can flow without any problem. But the problem is that now if I change the orientations of this word line, this I3, if I flip the orientations of I3, then the action will pick up one minus sign. Because if we change orientation, I mean entire things will have minus sign. So in order to fix this minus sign, because otherwise I cannot glue these two again. So this with the plus path integral, this is plus something, and then from here it's minus something. This I don't like. So I want to have a universal plus along this line. For that, on the I3 side, I have to do this redefinition. Maybe this is not, maybe there might be another definition, kind of change a variable, but this is kind of minimal one we can think about, think of. So clearly if we do, then I gives another minus, and then this will just cancel this problematic minus. So then practically, more concretely what happens is that on the I3 side, since this side I flip, which was blue originally, blue, but this becomes red, but red with an I here. So these wave functions that we attach on the final side is not functions of pi, but functions of pi and I pi. But suppose that originally this wave function was fixed, then we have to just introduce I, redefine. So if you don't like this mixed color, you can do the universally, this color flipping, and everything becomes blue. Then universally we can introduce I on this the second slot of these things. Originally this was slot for internal index 2. Internal index 2 and the internal index 1. But then this 2 side was flipped, and then the price to pay is introduced an I. So this is the trick. And then this trick is good, but not completely satisfactory, because I still have this issue that sometimes I have a bra state and sometimes cat state. And it's not obvious that whether they can be kind of rearranged to satisfy actual crossing symmetry. For that, for crossing symmetry, we should, it will be very nice to have a vertex operator. So which do not distinguish bra and cat in a sense. So in this way, I just define this to be my this vertex operator. This is definition of this V. I define V to satisfy these relations. So this I would interpret as the Worldline versions of state operator correspondence. I will mention later, but actually this kind of picture was also discussed in the Bayer's brain pattern model. So originally the state wave function were attached to the end of this double word line, which is just flowing homogeneously on one line. But after doing this machinery, a red line becomes blue line, and then we have outgoing and incoming lines. Since one line is outgoing and one line is incoming, it's kind of flow. And then we can regard this wave function as some operator acting on this flow. So that's the idea. And you can see that you can have the image that this is kind of again open strings, and then we open up this open string, and then a vertex operator is inserted at the edge of this open string. Somehow it's analogous to that. And another comment that I can make is that let me see. So I have to accelerate. So after doing this change, actually we see that the way that spacetime symmetry is acting on this vertex operator is adjoint action. And then, so this is kind of analogous to the passage from twist adjoint action to twist adjoint state to adjoint ones. And another thing is that since we have this v hat, we can consider trace instead of this transition amplitude. Actually, if you look at transition amplitude, if we want to realize transition amplitude in terms of vertex operator, we have to cook up this kind of things where tau hat is actually flipping the sign of pi. We have to do that. But actually, we can also do the other ones. And then at the level of two-point functions, we can regard this as actually this is transition function, so it's kind of wiped my two-point function. But this is slightly different, so probably it's Feynman two-point function. So this picture we have in mind, but we haven't successfully showed this kind of connection clearly, because for that, it seems like we have to do some proper wig rotation in twistor space, but that we didn't manage to understand yet clearly. But anyway, the picture that we have in mind is this. And then, and next about free theory, using trace rather than this one is just okay. So about the free theory, using vertex operator, everything just okay. So then at the level of free theory, but use trace and the vertex operator is good. So now we can continue, we can proceed to the interacting case.
I have a technical remark.
Yes.
Can you choose the picture of you to be in a different location? Because I think you use this corner for formulas, and sometimes you cover the formulas.
So
we cannot see some formulas because your picture is covering it due to this Zoom thing. Can you change your picture location? This corner,
I see.
yeah.
So yeah, before proceeding to the fully interacting other situations, I have one more comment about this vertex operator. So far, we worked for vertex operator as matrix element given by this formula. This is scala 1. But actually, we can also work really operator form of vertex operator because this is matrix element. So we can have a simple passage from this matrix element to the operator using this Wigner-Weyl transformation. If we do so, then actually, funnily, the function that we have is this kind of delta function. And this delta function is somehow looks like instancellation. But because if you just look this part, this is a 3D instancellation because there is no z coordinate. But at this time we have also this part. Somewhat weird because everything is real, but here I have an imaginary number. Maybe this again tells us maybe that for proper understanding or proper treatment of everything, maybe we have to complexify things. But we don't have a yet full understanding of this. Okay, good. Then now we are in the position to propose this kind of worldline higher spin gravity prescription. So worldline higher spin prescription that we propose is that higher spin gravity, the connected correlation functions of all field scalar or spin S, but the connected part should be given by this vertex operator insertion and the worldline integral over it. And then this permutation should be given by all possible permutation. So if you like, it's like essentially, so we add all these points in the here, and then in this gray box, in gray region, we connect this blue line in all possible different way you like, but it should be still connected. That's the only rule. Then actually it should be this much of possibility, and each of diagram will have this shape. And clearly I can, instead of this line, I can write more around, and then it will have this shape. And this is, so on this world line, we have to do this world line path integral. And this world line path integral is simply just boils down to trace expressions. So here, the reason that I did all these things, also introduced once again this path integral, is to show the similarity with the string theory. I think it's quite, at each step, we can just follow what we do in string theory. Then I think it was
I
get
had
the
so
reasonable
in
result.
this previous formula,
Yeah.
trace is good. Can you also see star product?
I think I didn't work with the star product, but for the star product, probably we have to work with this operator form, and then or actually this is not really operator form, but the symbol. So at the level of symbol, it should be star product indeed.
So
So
it's
then
the same formula as this zero form charges that Per Ergin et al. Introduced. We computed with Slava.
yes, but it had exactly this form.
Yeah, it's a trace of star product of several things that are Gaussian.
Right. So it was Gaussian. So I tried to understand, actually make the connection with your work and also Per's work. I think it should be in the end technically the same thing, but I could not yet clearly make the dictionary. But indeed I think one way or the other it should be connected, I think. So I have some comment on it later on. So this is the proposal, and then for the vertex operator, actually, I told you that there are undetermined constants C plus and C minus that can be eventually fixed by making use of some dual parity map, some sort of super selection rule at the in terms of dual parity map. And with the eigenvalue of this dual parity map, we can select type A and type B theory. And then type A and type B theory vertex operator is given this way. Type A is like this, and type B, actually we have a spinning case, and also pseudoscalar. So then with that, we can compute the AdS-4 correlation functions. Then again, this is just a trace of, so rather complicated trace, but anyway, it's trace of Gaussian function, so it's just Gaussian integral, not that complicated. And this was cosine blah blah blah, but we know that everything can be splitted in terms of Gaussian. So that's why we introduce Gaussian, and we compute everything, and then we make certain projections on this Gaussian trace. Then actually we obtain all good result. So we could compute, and we have some nice structure emerging at each time. And then we also have some full jet expansion, which has some nice combinatoric origin and blah blah. But here the main question, some question appears. Is it or is all this data reasonably physical one? I mean, all AdS-4 correlation functions are reasonable one, good one. Actually, I think it's not, because actually if you compare with the string theory, or just think that also both in string theory and in this case, vertex operators satisfy free equations. So our vertex operator, we checked that it satisfies a Bargmann equation or Klein-Gordon equation. In string theory case, vertex operator plane waves, it satisfies free equations of motions. So if we put in the middle of ADS, where interaction takes place, actually it's inconsistent. It's just contradictory. So I think the vertex operator should be inserted only on the boundary where effectively things become free. Otherwise, the formulation will break down, I think. Just doesn't work. So I think in the same way, string theory, we compute only scattering amplitude, but we do not compute any correlation function in string theory. I think that's the same things. So by making some close analogy with the string theory, it was helpful to understand what's going on here. So we see that so instead of tau and sigma, we only tau, and then position variable x mu here is kind of pi, and string state is this functions, and we have pi, and momentum is kind of label of this string vertex operator. Here AdS point is the thing, and then we know that the momentum should be on shell, so that kind of thing is similar, analogous to the boundary point. We can naively consider Z to be interior point, but we have to send it to the boundary. Otherwise, we see some contradictory situation. And then we have the plane wave, which is the vertex operator, while we have the other thing. So, and then boundary limit. If we take the boundary limit, we get all good result. So I just took the type A spiness example, the type A example, which is simple. And then for endpoint function, we can compute, and then we get what we get. And then this is reproducing that many people have worked out and found, and we could match the result. So some remark again, this CFT clearly, since we are computing only the correlation function in the limit, the insertion points goes to approach the boundary. Effectively, we are computing CFT correlation functions. So then we have to go to this picture, the higher spin ON CFT duality. So I will accelerate. So the conjecture, yes, Sejgen Sundel and the Klebanov Polyakov, and then many tests were done by Zombie and Yin, and many other things. But among other things, the Bear's work and also Zhenya and Slava work seems to be very relevant in our case, because I think technically many things are similar, and then even though the superficial level things are similar and also different, but I think probably conceptual, if you look deeper inside, probably same mechanism is working, I guess. There's another thing that we can also note is that the CFT operators that Sejgen also Zhenya worked out, so this was CFT result, just some preparation step to compute the correlation function and to compare with the ADS side stuff. So they nicely wrote down this generating functions of spinous current in type A case, or free boson case if you like here. So then actually we see that this expression has a strong similarity with the vertex operator of our case. So our case probably we have to take Z goes to zero limit, but then just this term disappears, and this we have to renormalize. Then without this and that, this is just plain wave, and this term seems to be same thing as this, and this term seems to same thing as that. So somehow at the operator level, without even correlation function level, operator level, or current level, there is some kind of relations that we could observe. Another thing is that this is probably Zhenya mentioned. Also the Colombo and Sundar and also Zhenya and Slava have done a similar type of computation using this the twistor joint field B, and then take the trace with the star product, and they obtained the good CFT correlation functions. But I think interpretation is a bit different, and computation to a certain extent is a kind of similar, and there are also technical difference. It's a bit hard to assess to just to quote the result here. So here the idea was that B should be the bulk to boundary propagator, so it carries 2 points, bulk point and boundary point, and also so this is also the key difference from our vertex operator. Otherwise, computation is both based on Gaussian integral. I think that's kind of same thing. But here also the other thing is that this bulk point, which is common point, the fate of this one, so that somehow decouples automatically and should be set to reference point. So that's the kind of difference. And brain patterns, technically, I don't have much to say, but I think conceptually many things are in common. Our work is in common with this work with, of Anquist and Sundell. So here they have in mind of this emergent theory is actually n singleton theory, and n goes to infinity becomes the tensionless limit. While if we take the finite n, in particular 2n, n equal 2, which is 2 singleton, which is higher spin gravity. So I think practically it's kind of proposing same thing, but here is they are working as P2R. So not this four-dimensional case, but they had any d-dimensional proposal and didn't do, I mean, the vertex operator they proposed, but that's more kind of formal and they didn't do any kind of correlation function computations. That's the main difference. But another super interesting aspect is that they pointed out that all these kind of things can be also formulated as a topological string, which is nothing but Poisson-Sigma model. Also, our model can be reformulated as Poisson-Sigma model. This is just Poisson-Sigma model, but our model is a super simple case where this mu part is just constant, which is nothing but the inverse of the simplex 2 form. So actually the model then can be just regarded as a kind of string theory, like, I mean, the topological string theory, where the action is given by PSM. And then we don't need to do anything more. I mean, then what we need to check is that whether PSM picture will provide a more interesting thing that rather than the worldline picture. Clearly, maybe summation over worksheet topology, and in doing that, there are some subtle cases. For instance, if you do this kind of thing, PSM will regard it as annulus, like one loop. But in worldline picture, actually, this is has a somewhat ambiguous situation. So we have to make more prescription in the worldline picture. So there are a bunch of these kind of things probably need to be clarified later on. Other thing is that also these fractional brains, which is that since we, especially when we increase the number of lines, actually I didn't mention, but we try to increase the number of lines instead of double line, but multi-line case, like this n picture in this large n case of string, the brain pattern case. Then I think some interesting picture appears due to this fractional brain. So then the target space is multipled, but still it has some kind of Z2 orbifold singularity. Then because of this singularity, this open string can be just anchored on this singularity. So there is some mechanism which we can profit from it. So that's, I think, I don't have much time, but maybe we can tell later on if you like. I think it's something similar to this multi-particle algebra that Vasiliev proposed. So this is the last slide, and loop will be again found as is proposed in this work, in this presentation. Loop is not just introduced because we just defined that everything is just a connected diagram. There is no place to introduce loop. But probably if you introduce PSM picture, then maybe loops are more natural. And then we really actually have to compute and see and check whether it actually gives non-trivial result or not. This kind of thing can be studied in the PSM side. And then we can also do the unoriented theory, like the unoriented string. We do exactly unoriented this double line. Here we introduce the line blue and red, but like uncolored case. Then will be unoriented this word line. that will lead to the actually minimal Vassiliev theory. And then finally, so we can do, I think we can very straightforwardly do the same thing in DS. Actually, we have some progress already. And then hopefully we can try to apply the same thing in flat chiral higher spin case. And ultimately, it will be fun to see the theta dependence. Actually, we spend a lot of time to see that whether there is any room for theta dependence, but actually we failed to find it. And now I think that probably we have to modify this theory in a certain way so that it incorporate this theta dependence, which will be eventually due to this Chern-Simons matter coupling, Chern-Simons coupling. Okay, thank you.
Thank you.
Euihun, can you go back to this last point? Because, really, yeah, this theta dependence. Because, in fact, part of this is known because, first of all, with Alexei, we showed that these traces are somehow unique invariants of higher spin symmetry. So therefore, if you know how higher spin symmetry acts on your states, you can recover the entire thing because these are unique invariants. So for sure, what you computed in the paper are these traces, because that's unique thing that is higher spin invariant, and you got the right answer. So kind of you can reverse engineer. But the thing is that these traces do admit a deformation that is parity violating, blah blah, etc. And at least to the first order, this deformation is driven by so-called FFS cycle. This is Felgen-Scheuchet. And this guy admits a worldline interpretation, which was worked out by Thomas should know better, Seoul and Grady maybe. So you just need different boundary conditions. So the usual propagator you use, you need to replace it by with anti-periodic, I think, boundary conditions, and this will reproduce.
Only that.
Yeah. So, but this will reproduce only first order corrections. So then you have a kind of two results you need. You need the fact that traces can be deformed in a way that is consistent with the full higher spin symmetry, which is now L-infinity algebra, than just... So
in that picture, you keep the kind of this vertex operator part untouched, and only you deform
well,
trace?
I think for sure we don't know, because invariants don't know what you want. So invariants just tell you that if you plug something in, they're invariant. But for example, in this paper with Didenko, one question was what to actually to compute invariants on, and at least in that case, bulk to boundary propagators were kind of a simple suggestion. So here, I don't know for sure, but you can take the vertex operators you already have. But the thing is, trace invariants do admit a deformation, and to the first order, this deformation is easy to implement within worldline formalism. It has been done in a sense, because these papers by Seoul that actually discuss how to generate this cycle via worldline stuff. So at least to the first order, you can capture this theta dependence. High order,
that would be fun to see how it works indeed. Well, thank you. Yeah, I will definitely try to understand the directions. I was having in mind doing some modifications on the worldline action, because it's essential worldline action is just PDX type, and then that action again we can deform with this, like we're gonna deform oscillator like stuff. So that can be also probably done at the level of worldline actions.
Yeah, it's not unrelated, because this FFS cycle is exactly the deformation of the Weil algebra towards deformed oscillators.
Yeah.
So, I mean, in any case, all these deformations of higher spin symmetry, they're somehow related to deformed oscillators, one way or another.
The concern that we had is that if we deform, I think AdS symmetry will be gone, right? It will be
No, it's just, I mean, if you look at the same Vassiliev equations, so it's not flat connection, it's proper L-infinity algebra. So higher spin symmetry as an algebra gets deformed. So, I mean, it acts via these multilinear maps that are field dependent, etc. So with some L-infinity algebra, and only to the leading order, you have simple, I don't know, adjoint, twisted adjoint type things, but then they get corrected. But invariants can also be deformed to remain invariants of this full symmetry.
But the AdS algebra also deforms, no? As a subalgebra of the highest one.
No, as an algebra, no, but its action gets deformed.
Maybe I ask next question. So the fact that the correlators are somewhat unique, does it suggest that you should get the same thing also after loop computation if you manage to define it?
Loop computation.
I mean, if
So
one could, yeah,
yes,
maybe you can say your thoughts on that.
yeah. The hope. So if I can, so the good point of all this machinery is that if we can define one loop correlation function, for instance, in some way, you can try to compute it.
Mm,
But whether we can define in a consistent way is probably the question, the whole questions. At this picture, you can see that not obvious whether we have to, maybe for one loop, we have to add just a circle here, or maybe circle
mhm,
and attached, and then attached here. It's not super obvious. So it's all the problem. The issue is the finding the consistent prescription.
mhm,
Once we are almost sure that okay, this prescription should be the right one, I think computation is relatively easy, hopefully,
mm,
and compared to other other method,
mm.
and then we can try. But we know that at least without any theta deformation, there is no loop corrections. So probably not, yeah, all those things should be somehow proved to be trivial.
No, Euihun, sorry. I mean, you have papers yourself. If you take even spin spectrum, there are corrections.
Ah,
There is
yes. So
portion of
that's another kind of possible things. But that will be
So
some universal shift toward this kind of things.
you will be basically imposing some constraint to cut some of the part of the spectrum, right?
Yeah, ON model. So it's like minimal model. Minimal
Mhm.
model loop effect is not completely just trivial, but in a
Mm.
sense, it's kind of quasi-trivial because from yeah. Anyway, so there is something that we can do. So some minimal check we can do. But the more non-trivial check can be only done for the theta dependence, I think. Yeah.
One more nature of question is whether, I mean, one could generalize this naturally to higher dimensions using different set of variables. So the difference would be that you need some extra constraint. It will not be just PDX type action, but you will
Mm,
have some this hot dual constraints you can impose as kind of Hamiltonian constraints, right?
right.
So the then in principle, I mean, also the correlators eventually, if you have to compute them as a trace of star product, and again, we have the machinery, we can do that. So, what is kind of making a big difference in terms, except for just simplicity that you don't have constraint here? Is there any special dimension property that you see?
I don't know, but I think just technically becomes more and more challenging. So this is really simple,
Mm-hmm.
but other ADS5 can be the next thing one may try. And then we should keep just a certain number of constraints. And then quantization will be slightly more non-trivial. So here it was trivial quantization, but there we
Mm-hmm.
have quantized constraint system. And for that, maybe we need some BRST, blah, blah. Yeah, but if you just go through everything, in the end, everything should be based on same kind of mechanism. So I don't think there is more genuinely more difficult thing aspect of
Yeah. So in AdS5, it will be Euihun constraints that you can implement, and then it's kind
yeah.
of simpler compared to general T where you need three constraints.
So
And you have a deformation parameter in principle. So I guess you have also non-trivial quantum correction.
that yeah, that might be something. Then yeah, that's another new aspect that we can think of indeed,
Mm.
the deformation parameter. And also, so something that I'm not yet completely satisfied with is this I stuff.
Mm.
So I
Mm.
think this is something to do with this Klein map. So because of that, actually we get that adjoint representation out of twisted adjoint representation. So I
Mhm.
think this is also should be relatively straightforward to show and then eventually clarify. because here I decide to just to choose this pi and xi variable because that's a simpler one in this computation. But the a more natural variable for classification is this y variable, which is given by some linear combinations of this pi and xi. And then I'd like to understand better also that aspect, how this can be connected to massless.
But do you know how high spin symmetry acts? Because you have kind of the right multiplet, all these massless fields of all spins.
Yes.
So higher spin symmetry must act on this. As long as you know
Right.
how it acts, the fact that these traces they have star products in it, etc., should be obvious then.
Yeah. Yes.
So I don't see star product, but I feel like there is no way out because there are unique invariants. You computed something, it gives the right answer, so it must be this invariance. But there,
So here it's a bit different. So in the usual way is that higher spin state is again functions of y, and then the higher spin algebra acts as a kind of this twisted adjoint action, right? But here it's not like that. Here we just have a higher spin, spineth generator, which is already differential operator. And then higher spin state is functions of pi. So I think it's same thing, but just different representation, if you like, or different model, different realization.
Yeah, this looks like a normal conformal action, this etc. So it's okay. In order to compute this trace invariance, in any case, we had to map them to a joint because trace is invariant under joint action.
So in the end, so that's why we end up with the adjoint stuff. After these introductions of I, we end up with adjoint.
Yes, right. So this is how higher spin symmetry acts, right? But it has to have star product in it. I mean, what is this commutator? It has to be star product. I mean, there is only one way how higher spin symmetry acts on the function of 4 variables in it.
Yes. So you can, this is star product. Yes, this should be star product. I need to think a bit more about that. Because originally we begin with everything doubled.
The doubled in what sense?
So you see that in order to compare with the Y oscillator, we have to pick up only one set of pi alpha and the Z alpha. So this will be give Y alpha and Y bar alpha. But we introduce two external label. So we begin with the doubled set. But I think one way or the other, it should be all just arranged in a way that it should be compatible with the picture that we know in massless theory. But the technical side, indeed, I need to work a little bit more to clarify all these connections. But I agree that I think it should boil down to the same thing. I think the picture that I want to deliver is the picture itself, this worldline picture and string theory-like picture, which works well in this higher spin gravity side, and it clarified quite a lot to me, at least, many aspects.
Yeah, it feels like it's very simple, but answers to some conceptual questions. That's my feeling, at least.
Yeah.
But also, when you say that the interaction has to happen only at the boundary, this is a bit confusing somehow. If we have somehow built the full theory and it just happens to have only interactions on the boundary, would that...
No, interaction will be in the Berg. But like in string theory, we know that the string theory is interaction, it will be everywhere, blah, blah. But we can compute only scattering amplitude in a sense. We cannot compute using vertex operator. We cannot compute correlation functions.
I see, because it's not formalism somehow gives invariant answers only for those.
Yeah, so that's why it will be fun to find out the beta function analog stuff in this worldline side. That may give us some kind of slightly offshore stuff.
I could go into bulk because this.
Yeah, so that's in a sense kind of slightly offshore. Not really offshore, but anyway, it's has some information.
More non-trivial would be trying to find something like string field theory for this.
Yeah, that would be also fun because again, so what I find is that this is really like open string. So you just you fill inside here. It's like topological, but it's open string. So everything can be obtained out of these 3-point interactions of this topological open string. So then maybe some open string field theory like method may work. But this theory is a bit conceptually it's a bit puzzling. It's too simple. There is no whatever symmetry to use and
Right, but there is just infinite symmetry, no? So
no, I mean the
that's why
gauge
it's simple.
symmetry.
Okay.
Yeah.
I have maybe one thing I just remember. So when you solve equations of motion, okay, when we solved back then equations of motion, it's just covariant constancy condition, or twisted. So you solve it in the usual pure gauge form, and then you see that when you compute trace, this gauge function dependence, which is the only way coordinates enter, it just disappears from the trace because you have like g minus 1, something g minus 1, something else g, etc. So I'm pretty sure, I mean, once this relation to star product is established, the same thing should happen for you. So interaction takes place nowhere. I mean, this bulk point or boundary point completely disappears. Yeah, in fact, there was
but here you see that so in our case vertex operators involve only one point, which is a priori Berg point, but where is it? Yeah, I mean just this field, right? This kind of field, just Berg point. But what we are saying is that if you keep this point in the Berg, then it will not be consistent one. So we have to put that on the boundary. So in this way, actually, in our picture, there is no Berg point in the end. Or if you like, we have this picture, yes. So essentially, this will be really on the boundary of AdS. And then insertion point, this should be, I mean, we can put inside, but that will be immediately inconsistent because it satisfies free occasional motion. So we have to push to the boundary. And that's it. And there are no Berg points in these expressions. So because that will be sent to 0 all the time. That was the point that I wanted to argue.
Just one more simple, I guess, question is related to the, so basically in the 2-point function, you get two contributions from what I remember. It's basically one is the bulk to bulk propagator, and the other is bulk to boundary and then back to bulk, right?
Yeah.
That's somehow one.
Yes. That's right.
And then you mentioned mirror, but effectively, so I guess it's a free theory. You may have some sort of geodesic propagation. So there's only one point in the boundary where it kind of comes back to the given 2 points. There's only one point in the boundary that you would come back to there, or every point in boundary could, in principle, do contribution.
I don't know. So it's like this. So this is AdS. So we have a point. So naively we have this. This will be the D, if you like, this one. But there will be another contribution which will be this.
Yeah,
That will be
and
actually coming from the mirror image. Yeah.
Exactly. So it's kind of there's only one point if you think in terms of mirror image.
Yeah. I think it's only one point.
Right. It's
Yeah, I
straight
think it's only
geodesic
one.
propagation. So yeah.
Yeah. So I think it's in matter of interpretation. So I think yeah. So we can also do the antipodal point, which is outside of this Poincare chart. But for that there will be a bit weird. So the 2 point is this, and the antipodal point is the other side, and then some other. In that case, it's not across some bouncing off from the boundary, but coming from the
going somewhere.
Yes, from the opposite directions.
The reason I asked this is because I think there was some sort of general prescription that you can define bulk-to-bulk propagator, but you have to also integrate over the whole boundary contributions that bulk close the boundary and pay.
Yes.
This is maybe simpler setup where you have free tier and there is only one point contribution from the boundary.
No, these are just different representations. So you need to work out green function with specific boundary conditions. So that's why HUD has this image term. But on the other hand, there is a like spectral representation as the integral over two boundary to bulk propagators glued by some density. But again, it should contain information about boundary conditions anyway. So these are just different representations of the same, I think.
Yeah, if you had that in mind, indeed, yeah, it's the same thing, but
Maybe I need to think a bit more to understand that.
but otherwise there is the physical boundary maybe also may play. I mean, this is also physical boundary, but with other kind of boundary, they may behave differently. But in this case, just ADS covariance dictates that this is the only possibility.
And one more just question is that so I mean, this is very much tied to ADS, but in principle, one could do the same in flat space, for example, but there's no boundary. Or how would you? Is there any logic how this would extend to flat or de Sitter even?
You mean this means the mirror stuff or
No.
two-point
I'm the
function?
overall picture. Yes, the general construction of the worldline.
Yeah, I think it can be done. Originally, if you look I mean, the Weinberg book is just flat space-time, and we can also do the jitter and any actually. Well, actually, the jitter ADS and flat space-time is the only possibility. Otherwise, we cannot fully determine the field. So actually, what
You're
we
using
did
all of
already
the isometry.
we already had some result about the jitter. In the jitter, we have the same kind of pattern, but the interpretation is slightly different. We have alpha bar issue, and then flat space time, I think we don't have this ambiguity of two terms.
So the ambiguity in the sitter is related to the alpha bar.
Yeah, ambiguity in the jitter is related to the alpha bar, which is again related to the antipodal point. And flat space time, I think we don't have any ambiguity. And in ADS, we should not have any ambiguity once a certain boundary condition is imposed. But in higher spin case, we do have still some sort of ambiguity. That is a different kind of ambiguity because you see that it's unphysical. At the level of 2-point function, we cannot distinguish. So the theory with the C plus, I mean, with the same number, same C plus square and C minus square, but the different ratio cannot be is not visible physically. So the reason is that actually the Hilbert space, one particle Hilbert space contains spinous space twice. But that's so 2-point function level it doesn't matter because actually they are orthogonal to each other. That's why we have no cross term like this. But if you go to the interacting case, actually they if we put both of them, it becomes a bit messy and leads to unphysical situations. So that we select based on this kind of dual parity map stuff. We make selection.
Yeah.